and thank you for the invitation. As the title says very clearly, my recent agenda is focused on the idea of combining a very powerful idea in economics, which is the idea of markets, of competitive markets, and the good properties they have when they work well, and combine this powerful idea and with assignment problems in which money is not accepted, or it doesn't exist, or it is repugnant. Its use is repugnant, as Alvin Ross says. Examples include organ donation, school choice, so the allocation of kids, of children to public schools, the roommate problem, so the allocation of people to a roommate, indeed. The allocation of doctors to hospitals and so on, in which, in theory, money doesn't play an active role. But the idea is to create pseudo-markets, so markets with monopoly money, if you like. I will explain it later during the presentation, but I think that the idea is quite clear and easy to understand. Let me say first that my co-authors are Federico Echenique, a great economist from Caltech, and Jun Zhang from Nanjing Audit University. I was already talking about examples in which we talk about allocation problem, jobs to workers, courses to students, course to family members, organs to patients, and so on. In these kind of problems, we have several desiderata. We are not going to talk about incentive compatibility, strategy proofness here. We rely on the idea that in large markets, manipulability, profitable manipulability, is quite tough. There are some papers showing that that incentive compatibility in asymptotic sense applies to competitive markets. Our normative desiderata in this paper are going to be efficiency in the Pareto sense, fairness in the sense of no envy. So basically, I don't want an allocation in which agent I envies what agent J has. And finally, time permitting, then I have to see how it goes. Or maybe I will go very fast to this last part of the presentation. I will talk even about property rights. Okay, so pre-existing property rights, or endowments, if you like. Okay, the idea of pseudo-markets is not ours, of course. Let me mention a paper by Hillan and Seckhauser in 1979, in which they already suggest this kind of idea. Okay, we provide agents with a fixed budget in monopoly money. When I say monopoly money, it means that it doesn't provide you utility per se, unless you make a collection of monopoly money. For some reason, you are passionate about monopoly money. It's not useful for you. Outside of the allocation mechanism, it's not useful for you. It's not going to give you utility. But it is going to be useful in order to buy goods or to buy allocation probabilities. Okay, so this money allows you to purchase fractions or probabilities of objects at given prices. And how are those prices decided? Well, let the market work and arriving to a competitive equilibrium. So this is the idea. Again, the seminar paper by Hilland and Hauser. Interestingly, there were no subsequent papers after that. Okay, this is a Journal of Political Economy paper, so it was quite an important paper. However, for 30 years or so, it was kind of forgotten, and I think that the main reason for which this kind of pseudo-market idea was not put into practice is that it is difficult to reconcile with the fact that many of the allocation problems we are talking about are affected by constraints. Okay, you know, protection of minorities, some sort of privileges or objectives that the policymaker might have, and so on. And a market per se, in which the only variable you can play with is income, may not be able to accommodate them so easily. But in recent times, and I have to say that I'm one of the researchers that are extending the idea of pseudo-market to the presence of constraints, we have been able to slightly modify the original Hilland and Hauser idea in order to accommodate constraints. As an example, a paper with that I co-authored with He, Pichia, and Yang, that was published in American Economic Journal Micro, well, got a prize, the best 2019 paper. So it was kind of you know, relieving for me that this was an interesting idea. So the idea of Hilland and Hauser, as I was saying, is very simple. Okay, there is a finite set of agents, finite set of objects to allocate. We suppose that we have enough number of objects, and then basically agents have preferences over the simplex. Okay, here, as you can see, do you see my mouse cursor here?
Yeah.
Okay. It is the extended simplex, but at the end of the day, in equilibrium, it's going to be an equality. Okay, but preferences are defined on the extended simplex. Okay, basically a utility function. In the original Hilland and Hauser model, those utilities are of those preferences are of the expected utility form that is linear. And so basically the idea is to proceed to an assignment, which is an assignment of probabilities over objects, and that meets the feasibility constraint. Here we are using the assumption that there is one unit for each object. This is without loss of generality. So basically here what it's saying is that total demand cannot exceed total supply for any object. And then basically the idea of Hilland and Hauser equilibrium is the typical idea of competitive equilibrium. Okay, and it says there exists. So this paper says, states and proves the existence of such a competitive equilibrium. Not every equilibrium is efficient. Recall that the consumption space is bounded, so there is satiation. So the first welfare theorem, in order to make the first welfare theorem work, we need to make a selection over the equilibria that we might find. So there could be that an equilibrium is not efficient, okay? But an efficient equilibrium will always exist.
Just a clarification, Antonio. The point is that in these pseudo-markets, the idea is that in equilibrium, what you obtain is you buy like probabilities of obtaining each object that is available.
Yes.
Okay, so So basically, you are given some income, some monopoly price, some monopoly income, and you can buy probability of getting whatever the objects that are available. So in this case, in the jobs, that
at the end of the day, by the virtue of the Virchow von Neumann theorem, you know that all those probabilities are implementable. So basically, when I say that it is implementable, I mean that there exists a lottery over deterministic feasible allocations that are mathematically equivalent to the probabilities that are assigned to each individual.
Okay.
So there is no problem when there is a single object that each agent is going to obtain at the very end. Okay. There are problems with the Virchow von Neumann theorem when we have multi-unit allocation.
Yeah.
Okay. There are papers about that. I think there is a paper by Vora, for instance, and co-authors, Guyen, Vora, I don't remember the third author, in which they talk about that and they say, okay, but in big markets, this is not going to be a problem. They find a very fast asymptotic equivalence between feasibility and implementability. But indeed, yeah, you are right. I mean, it's not easy to see how in practice you are going to implement this. But let me just tell you that someone else decades ago already proved it is possible. And then I continue with my presentation. But of course, with multi-unit allocation, this is an issue. But indeed, we are going to take that into account when we model the constraints already. So that we are going to characterize the deterministic allocations that meet the constraints. Okay, this is the technically difficult part. And for each case that you analyze, the most important thing you have to do is you have to identify the set of deterministic allocations that are feasible and implementable. So, well, if they are deterministic, they are implementable, sorry. And then you take the convex hull over the feasible deterministic allocations. Okay, so wrapping up, the important thing is how to model the constraints. And this goes case by case. There is no general way to model the constraints. Depending on the problem at hand, you will have to model it in one way or another. Indeed, we have several discussion sections depending on the kind of problem that we are taking into account. But you know, in order to sum up, I just want to say that we already take implementability into account because the constraints already include lotteries over feasible deterministic allocations. All right? Carmelo, are you there already?
Yeah, I see the point.
Did I kill you with the too long explanation? Okay, next time I will provide a shorter answer. Thank you anyhow for the question, which I think it was fair. Okay, so basically the idea is a competitive equilibrium idea. Okay, and in their paper, they do not give agents an initial endowment. They give them an initial budget. And indeed, the problem is that the presence of endowments instead of budgets may lead to inexistence of competitive equilibrium. Indeed, again, the idea is that the consumption space is bounded, and there might be a problem of continuity of the demand functions or correspondences. So, okay, but I'll talk about that later if time permits, because I've already spent 20 minutes in the introduction. So, okay, this is what we do. Okay, we take the Hill-Alexander idea and we extend it as much as we can. Okay? And we are going to consider families of constraints, linear constraints, finite number of linear constraints that apply to several cases that are interesting in the allocation problem world. So that is in Carmelo and Antonio's economy. For instance, the roommate problem, allocation problems, rural hospitals, and so on. With and without endowments. So time permitting, I talk about what we do when we have also endowments.
Antonio, may I interrupt you for a moment?
Yes, Luis.
Some time ago, I came to a seminar given by this guy, Canis Prendergast, who is in Booth School. And he had been working on creating the markets for feeding the poor, right? And he gave a very interesting talk about how to create markets in which you allocate the surplus that are given by several restaurants and several institutions in such a way that you actually get an efficient allocation of resources. So perhaps it's also a good idea to look at this literature, isn't it? Or...
Pendergast.
I'll send you.
We might, I was going to ask you that. Could you send me the link? Because we are looking at, we have a lot of bibliography, but maybe we missed, this is possible, maybe we missed.
Nice application, right? Okay, thank you.
Okay, please pass me the link. Okay, so the key idea here is, of the whole presentation, is we have to price the constraints, okay? We do not price the objects per se. We price the constraints, okay? And the way we do that is not that easy. So we will need some processing of the constraints first, okay? We will see, I will show you what we do first with the constraints before we price them. And not every constraint is going to be priced. So we have to select which constraints are going to be priced and which constraints are not. The hint here is that we are going to price the constraints when they involve externalities, pecuniary externalities, okay? And prices are going to internalize those constraints. Instead, if you take, for instance, unit demand constraints, which are individual constraints, instead of pricing them, we are going to use them to redefine the consumption space. Okay. So some constraints are not going to be priced. Just keep that in mind. And some other constraints are going to be processed in a way that we are going to see very soon. So what kind of cases can we analyze with this kind of machinery? The first example is the case of rural hospitals. In the allocation of doctors to hospitals, there is a typical issue that is important politically, is that rural hospitals are typically, let's say that doctors prefer to avoid them. Yeah? And in the allocation problem, we have to guarantee, or from the point of view of the policymaker, we have to guarantee that at least a minimum amount of positions are assigned through these rural hospitals. Okay, we say rural hospitals could be any kind of hospitals that, for some reason, are not that preferred by doctors. So we are going to, of course, have upper bounds on the number of available positions, typical scarcity problem. But here we are also going to include a lower bound of the number of doctors per region, okay, or per zone, if you like, okay, or type of hospital. And this lower bound applies because some hospitals are under sea level, so you have to impose those lower bounds. And indeed, in section 4 of the paper, I'm not going to explain how we do here, but the idea is we process the constraints so that they are manageable in the way that I'm going to show in a few slides. and we obtain that by manipulating the upper bound, the original upper bound constraints and the lower bound constraints, we can characterize what we can price by a set of modified upper bound constraints. Also, another example is the case of course bidding or assignment of courses to students. And here, this is a multi-unit assignment. So here there is an issue on what is on the difference between feasibility expectations and implementability, as Carmelo was trying to point out. So we have to take care of be careful on defining the meaning of a constraint here. So among the constraints, there are upper bounds, of course, because there is no unlimited number of places per course, but also there is some sort of upper bound in the way you can combine the courses individually. And also there is a lower bound on the minimum number of courses that you have to take. Or if you are specializing in economics, of course, you have to take these mandatory courses. And then there are some other optional courses, but at the minimum, at the least, you have to take a few mandatory courses. Okay. And the idea is to price the upper bound so that the most desirable courses become expensive, and then demand overflows in order to accomplish with the lower bound constraints. Another interesting application of our problem, of our model, excuse me, is the problem of roommates. So who are you sharing the room with, right? Typically, rooms have to be occupied by two mates. And the idea is that students are both agents and objects here. Because we have to make pairs of students. And there are interesting constraints or peculiar constraints in this problem. First of all, the unit demand constraint. You are paired to a single other student. And then there is the symmetry constraint. If you are allocated to some student, this other student has to be allocated to you. Okay. And we show in section 5 that in the paper, I'm not going to show the details here, that even these constraints can be modeled in the way we propose in this presentation. And this is particularly interesting because it is known that the roommates problem may not have stable matchings. Okay, so the notion of stability, so no blocking pairs, may not be met here. However, we can find a sort of equilibrium in the sense of competitive market equilibrium. So, quote unquote, maybe forcing it a bit, it's another notion of stability. And plus, we are providing efficiency in the Pareto sense. So another example in which our model applies is the case of endowments in the allocation of office spaces. But the idea is that professors are, unless you are a newcomer, you already have an office. So therefore you have an endowment. So individual rationality constraints may apply here. And this might be taken into account. Our model deals with that as well. Okay. Finally, in school choice, we also have quotas for minorities. We have property rights that are not really property rights. They are priorities. For instance, the idea of neighborhood schooling. Yeah, you can apply wherever you want. But if another kid that lives in the neighborhood of the school applies there, this kid has priority over you. So if some of the if some of the priorities might be processed as if they were property rights, and they could be treated as endowments. Okay. And although it is not said in this slide, also in section 4 of the paper, we deal with quotas for minorities, soft and weak quotas. So the minimum number of students from coming from minorities in each school, the maximum number coming from majorities, etc., etc. And we also can process those constraints in a way that it accommodates our model. Things that we don't do is a maximization problem. Okay, it's not that we take a utilitarian maximization problem and we solve it subject to constraints. Okay, we just proceed to provide the possibility of obtaining some sort of competitive equilibrium. We don't show second welfare theorem. Luckily, however, I have a paper with Marek Pichia that is resubmitted in JET in which we already prove a second welfare theorem in this kind of allocation problems. So there is lots of related literature, as Luis was pointing out. There are even more literature that we have to read, but there is quite a lot of literature. We are not the first ones in thinking about markets, of course. You see that there are seminal papers about markets and fairness in general, Varian and Hillan and Zeckhauser, Buddhist for the course allocation problem, allocation with constraints, as you can see, Ehlers and Hafalir and Jemmeth and Gildrim and Jet paper, and so on, following papers. Markets with constraints. Let me stress this paper by Gould, Pesendorfer, and Zhang, quite a good one, very general. And problem with endowments, Mascoley, Hay, McLennan. So we are not the first ones in doing anything, but I think that we are providing a very general setup that might work for the problem that you have at hand if you are analyzing allocation problems. So let's go with the model. I'm already, it's 1:30. So I'm already having a vision of the future in which I go over the endowments problem very, very fast. So basically, we are going to let me tell you about preliminaries. Okay, our constraints, the kind of constraints that we are going to consider are linear and finite. Okay, so a linear inequality could be characterized by a pair of a vector of coefficients A and a number B. Okay, so this is what you have to take into account. Okay, where X is the allocation. This is a matrix. Okay, this contains the quantity that each individual obtains of each object. Okay, so a linear inequality has non-negative coefficients if this vector A is non-negative. And this does not need to be the case at the beginning. We are going to treat the constraints in a way that we obtain modified inequalities or constraints in which non-negativity applies. A linear inequality defines a half space. Okay, and the half space that lies below B is, is valid. So everything that lies below is valid for us, is feasible. A polyhedron is just an intersection of a finite number of closed half spaces. A polytope is a polyhedron when it is bounded. And two special cases of polytopes are the simplex and the extended simplex, subsimplex, that characterize individual consumption spaces in this kind of allocation problems. When the dimension is understood, we just skip it, okay? And we talk about delta and delta lower bar. So imagine that we were able already of identifying the allocations that are feasible according to the constraints. Okay, so here the superscripts are not referring to individuals; they are not referring to objects. So here, this x1 is allocation number 1, this x2 is allocation number 2, this x3 is allocation number 3. All of them are feasible. Okay. And a lottery over feasible allocations is just the set of all lotteries among the set of deterministic feasible allocations is just the complex whole. Okay, so this C is going to be the set of feasible allocations for us. As you can see, since it is a polyhedron, it can be characterized by a series of hyperplanes, and each hyperplane contains a perpendicular orthogonal vector. And this is the vector of coefficients of the linear inequality associated with its constraints. So, for instance, you take this one, A2 is going to be the vector of coefficients associated with this hyperplane here. All right, and indeed, it's going to have some role in defining the price later on. Now let's talk about, a bit about utilities, about preferences. So we already start by assuming that preferences can be represented by a utility function. Those could be, we are going to assume quasi-concavity and in some cases semi-strict quasi-concavity. What is semi-strict quasi-concavity? Well, this quasi-concavity with no plateaus to make it you know, small talk. So to plain a plain explanation or intuitive explanation. And in a specific case of semi-strict quasi-concavity is the case of expected utility. Okay, when expected utility, when it is linear. Then the economy is defined in a very standard way. Okay, it's a tuple that contains the set of agents, the set of objects, the consumption space and the preferences for each individual, and the supply for each object. An assignment is a vector in which each xi is a vector x, is a matrix x, in which xi is a vector of individual allocation of quantities, one for each object, and each xi belongs to the individual consumption space for agent I. Let A denote the set of all assignments in this economy. It is deterministic if basically it is assigning integer quantities. Constraints are often imposed on deterministic assignments, and this is what we are going to process. For instance, unit demand constraints, basically saying that whatever you obtain, it cannot exceed 1 in total. Supply constraints, whatever you give, it cannot take of some object, it cannot exceed what there is there. And there are other kind of constraints. Let me jump on this slide of what we do. A deterministic assignment is feasible if it satisfies all exogenous constraints. a random assignment is feasible if it belongs to the common school of feasible deterministic assignments, and this common school is a polytope. And therefore, it is characterized by linear constraints. So basically, we take this polytope, C, and this is basically the base of our model, C, okay, and how we process C. So constraints are already, so you imagine that you have already characterized how the constraints in your problem translate into the set of feasible allocations, okay? Once you have done that, and this is not an easy task, okay? For that, we provide later on in the paper several analyses, as I was mentioning before, roommates problem, rural hospitals, etc. So basically, consider the fact that we already know what C is, okay? And C is a polytope.
So Antonio, just start with a set of deterministic assignments that are feasible, and then you look for
the common school of them.
Of a common combination of the. Okay.
Yes. And all right. Okay. So in a constraint allocation problem, you have the economy and the set of feasible assignments, which is a polytope. In this allocation problem, we want to impose several properties. Constraint Pareto efficiency, which basically there is no other feasible in the sense of respecting the same constraints. Allocation in which there is a Pareto improvement. Okay, and there is also the weak notion of Pareto efficiency, which is the standard one. For fairness, let me just in this slide not explain with precision what it is, but basically the idea. So I will go over that later on in a further slide. But basically the idea is we want to impose no envy, but no envy might not be possible. So we will have to be happy enough with no envy among equals. So meaning agents that are treated the same by the constraints. Okay, in what sense? We will see later. So now the important part, what do we do with the constraints? We are going to do some processing of the constraints so that at the end of the day, let's say positive prices or non-negative prices apply. Okay, and recall that each constraint is characterized by a pair A is a vector of coefficients, and B, which is the number. In order to do that, and borrowing an idea by Balbuzanov in a econometrica paper 2019, in which he doesn't deal with pseudo-market allocation, but he deals with adapting probabilistic serial to the presence of constraints, priority constraints, for instance. And basically, he defines the same idea, this pre-processing of constraints. Instead of facing the constraints directly, first he constructs the lower contour set of it. What is the lower contour set? Well, this is the definition. It contains every allocation such that it contains every allocation such that there exists an allocation that is feasible, that is bigger in every component, at least in the weak sense, 2x. Okay, we will see that in a graph in the next slide. And the lemma is, or important instrumental result that we have here, is that there exists a finite set, which we call omega, of linear inequalities that characterize the lower contour set of the original constraints. Okay, with non-negative coefficients. And this is going to be important for the prices, the fact that we have non-negative coefficients. How do we do that? Recall that this was our original set of feasible allocations. What do? We include, as you can see, we include these allocations here, we include these allocations here. Why do we do that? Because there exists this vertex here that is bigger in every coordinate to every allocation that we have here. Okay, so everything in this area belongs to the lower contour set, obtaining the lower contour set here in this way. As you can see, we have provided a modification of the constraints. Some of the constraints survived. So this one characterized by A3 is already there, but some others were created new. In all of the new constraints that we are facing, the allocated coefficients are non-negative. And this is the kind of modified feasible allocations that we are going to explore here. And here is where we are going to use the idea of competitive equilibrium. But first of all, remember that I told you at the beginning of the presentation that not every constraint was going to be priced. First, there are constraints in which B, so the number on the right-hand side is 0. And there are constraints in which the number is positive. You cannot, since we already modified the constraints, so every coefficient is positive, you cannot have B being negative. So it's either 0 or positive. All those constraints in which B is 0 are talking about impossibilities. So whenever the coefficient associated to an individual and an object is positive for such a constraint, it means that it is impossible for this agent to obtain any positive quantity of that object. Okay, so we call it a forbidden object. And without loss of generality, we can assume that there is only one such constraint with B equal to 0. Okay, so we are talking about impossibility constraints here. Now, as for those with B equal to 0, first we are going to prune those that are just individual. Okay, you see, we have already taken out the constraints, the impossibility constraints, and now we are going to take out the individual constraints. An individual constraint is individual for agent I if it is if this agent is the only one affected. So for any other agent that is not I, every single coefficient associated to J for any single object is equal to 0. So basically, for instance, unit demand for agent I is an individual constraint. And we take it out as well. So we take out impossibility constraints and purely individual constraints. The rest, which are denoted as omega star, are those that are going to be priced. For each constraint, there is going to be a price. And what do we do with the constraints that we were not pricing? Well, they are going to be taken into account into the individual consumption space. Okay, so the consumption space is going to take into account impossibility constraints and purely individual constraints. Okay, again, for instance, a typical individual constraint is the unit demand constraint. Okay, no matter how many probabilities you obtain, they must add up to 1. So, okay, again, in unit demand constraints are individual and go to, this is an example, and go to the individual consumption space. Supply constraints, for instance, go instead to the omega star, so they are going to be priced. It's the typical price for some good. So each constraint is going to have a price. The constraint is a pair AB. Okay, let me insist. A is a vector of coefficient, B is a value of the constraint. And then for each constraint, we are going to have a price. Okay? So recall that we are not starting from a personalized price vector. Okay? We are pricing the constraints, and then we are going to personalize the price vector in the following way. For each individual and for each object, we are going to take every single constraint that can be priced, and the price that this guy is going to pay for this object is equal to the weighted sum of the prices for each constraint, and the weight is going to be the coefficient associated to this agent and this excuse me, and this object in such constraint. So, and now I can talk about fairness in a more formal way and precise way. Two agents, I and j, are of equal type if, one, they have the same individual consumption spaces, and two, every constraint that is going to be priced treats them the same in the following way. The associated coefficients are equal for individual I and for individual j. Okay? So for equal types, we are going to impose ambifreeness. Now, the standard definition of a competitive equilibrium is an allocation in which, well, it is feasible, it is utility maximizing up to budget constraint. We are going to normalize every constraint to one, okay? Every budget to one, sorry, here, like in Hiller and Seehauser. And so for each individual, what he obtains is what he wants to buy. The allocation is going to be feasible and moreover some slackness condition. So if there is some constraint that does not bind the equilibrium, then the equilibrium price for such a constraint is going to be zero. So as an example, if there is excess supply for some good in equilibrium, then the price for this good has to be zero. It's the standard slackness condition. So the main result, there exists a pseudo-market equilibrium which is weakly constrained Pareto efficient. Okay, weakly only because remember that when you have a constrained bounded compact consumption space, competitive equilibrium per se does not guarantee Pareto efficiency. But if you make preferences semi-strict quasi-concave, you can indeed guarantee the existence of a Pareto efficient, constrained Pareto efficient, and not in the weak sense. Okay? It's a strong constrained Pareto efficient allocation. And indeed, in every pseudo-market equilibrium assignment, we can guarantee ambifreeness among equal types. So this is the main result. Okay. As for applications, I invite you to go to sections 4 and 5, and you will see interesting way to process the constraints and make them priceable, and how to proceed, right? And then once you have that, the idea is, as I have shown you in the previous slides. And very fast, because I have 5 minutes basically, let me go fast over the domain.
Antonio,
yeah.
I was thinking about the idea of the pseudo-market and giving the monopoly price. I was surprised that I didn't see any allotment of initial income of monopoly price. But the idea is that, well, the point is that the role of the endowment of monopoly price is that eventually you will have to end up in one of the feasible allocation, deterministic allocation at the beginning. So that
you're going to find a lottery that is efficient in the ex ante sense.
okay.
Therefore, it implies that it's a lottery over efficient deterministic allocations.
Okay, so I think that this is the previous slide. When you have the definition of the pseudo, that's the point. This one in the first item, the point is that the price times the allocation is 1. The point is that you eventually receive one of the deterministic allocation.
But here, this X, remember that since we have taken into account the convex hull, so we have to take into account lotteries over deterministic assignments. Here, this X could very well be a lottery.
Okay. No,
No, we are talking about preferences over lotteries, for instance. Okay. So yeah, your optimal purchase could be deterministic for you. Okay. But that not need to be the case. It could be the case, as in Hill and Hauser, that you end up buying, I don't know, 2/3 probability for object 1 and 1/3 probability for object 2.
Okay.
And this is okay.
Is that the role of the income of the pseudo monopoly
this thing here?
one, okay, that eventually you are gonna get something.
Yes.
Good. Yeah, I see. Okay. Thank you.
So let me go very fast over endowments. Okay. So to this problem with constraints, you can add a special family of constraints, which is the presence of endowments. So individual rationality constraints, basically. And they are represented by endowment vector. But, since I have like 3 minutes to explain it, let me go very fast to the idea. The idea, and this was already illustrated in Hill and Hauser, is that an equilibrium might not exist if you have endowments instead of a pre-assigned budget. Why? Okay, remember that your consumption space is the simplex here. So basically, what can you buy? So on the one hand, you have the budget set, but what you can really buy is this part here. Okay? So if you rotate the prices, this is not going to change. So it might not, let me see, no matter how I rotate this, no matter how I rotate this, I do not change the budget set. But then out of a sudden, if I rotate it towards the red line, out of a sudden, the budget set jumps. And then you have the whole simplex for you. So the budget set, given that you have your consumption space is compact, the budget set is not a continuous correspondence on prices. So it might be the case that you prefer this allocation here that is super stream, but you can only arrive to this point, because no matter how you rotate, no matter how you rotate the prices, this is the maximum you can obtain, the maximum approximation you can obtain. But if you get to the point in which this rotates and is identical to the red line, out of a sudden, your demand jumps to this extreme. So there is a problem in that there is no apparent continuity of the demand correspondence. Okay, this was highlighted already by Hill and Hauser in a footnote. Okay, this is more deep analysis on something that Hill and Hauser noticed already. So what can we do? We can do the following. We can do the following. We can let me go very straight to the point. We can go here. Okay, typically in our Walrasian equilibrium, your money is equal to this, right? The market value of your endowment. Now, here, what I'm going to do is to give some weight to equal incomes. So imagine here there is a 1, okay, as in the original problem, the same income to everyone. So basically, your income is going to be a complex combination between what corresponds in the Walrasian economy and the equal incomes economy, okay, with an arbitrarily small, if you want, arbitrarily small weight alpha, but it has to be positive. Why do you need this positive? Because here, this guarantees that the budget set is going to be continuing prices, and then there is not going to be continuity problems in the demand correspondence, and you are going to guarantee the existence of equilibrium. And what is the price? And now the price that we pay, the researchers pay for that. Well, the price for us is that individual rationality is going to be met in some weak version, because it might be the case that your income does not allow you to buy your own endowment, and you end up slightly worse than at the beginning. So on the one hand, you obtain the standard properties that we had in the first theorem. So, you know, Pareto efficiency and equal type MB freeness. And on the other hand, however, individual rationality is obtained in some weak sense, okay? That is, the maximum you can obtain in this, if your budget set was not altered, and what you obtain in the equilibrium allocation, okay, this thing here could be higher, but only for some quantity epsilon. Okay, no matter how small you make epsilon, I can always find some alpha very small that allows me to satisfy individual rationality in this weak version, epsilon individual rationality. So basically, this is it. There is some related literature as well. Okay, let me mention Mascolay, this chapter, a very nice chapter in 1992. And some recent work by Hay and McLennan that, you know, they take slightly different versions of the same idea of slightly modifying the incomes, and this is what we do. Okay, this is basically it, because I cannot go to the rest of the proof for the lack of time.
Don't go fast. Don't go fast.
But this is basically the idea, and with that, I think I would be done. And I thank you for your patience. If you didn't like it, and if you like it and you have some questions, it would be my pleasure to answer. To answer if I can.
Okay, thank you, Antonio. I think that we have time for some questions, because it's just 59 minutes. You still have 1 minute.
That 1 minute was not enough for the group, but you could see.
Okay. So is there any question? I have several, but
I do have one. I raised my hand politely, but with the possibility of being out, and I just jump in. Well, Antonio, you did a great job doing the teaching, because I have to read the paper. Especially because you know, you claim that you can solve the rural hospital problem, but if you can solve the rural hospital problem, that means that your stability is actually not the usual stability that we use in matching, because
Indeed.
Rural hospital problem implies that if you cannot fill a position, you cannot fill a position in any stable allocation.
No, exactly. So when we say, remember that I say quote unquote, it could be as an alternative version of stability is not stability.
Wait, that's what I know. That's not the question. Then you claim that you have the one-sided envy, and this one-sided envy it makes me hint that you're going to treat individuals that are alike in the same way. So if you happen to have men and women, then you are going to care about women but not about men, and that's how you go to efficiency. That I get it as well.
Okay.
Let me go back to when I'm puzzled. You claim that you can solve Buddhist problem, the course allocation problem. But Buddhists have several problems there. For example, one of them is how to elicit the preference, because you have a combinatorial problem there, and you need preference and betting for each one of the possible, not courses, but schedulings. So that's an issue.
That's an issue.
And the other issue in Buddhist is that even if he has that information, he have a hard time computing the almost equal income general equilibrium that he computes, because it can go into local optimums and so on and so forth. So how do you solve that? I mean, is your refinement of the constraint enough to do this thing? That's my problem.
So let me go for the simpler cases first. What we know is that, and this comes from another paper of mine with co-authors. If you take a model of a pseudo-market that is adapted to priorities in school choice, and of course it's not the multi-unit assignment, right? Then there we show incentive compatibility. So even if we have this kind of constraints, the idea of incentive compatibility, Roberts and Postlethwaite idea, 1976, something similar, all right? This works in a pseudo-market even with constraints. How to elicit preferences? Well, in the unit demand case, this is a bit easier, right? Like kind of give me your von Neumann-Morgenstern valuations. Well, this is not the right question to ask to a standard consumer, but you know what I mean. So it's possible. For the multi-unit assignment case, this is more difficult, right? How to elicit the preferences, because there is a double problem. Okay, on the one hand, you could just go direct mechanism, but then the idea is how can a standard agent reveal preferences over sets? This is difficult. On the other hand, you could just go attunement process, like while raising an idea, right? Do not reveal me anything, and then I just do some sort of attunement, right? The prices of the constraints change according to what people purchase. But this is definitely another issue, because one thing is to prove existence, another thing is to prove that this attunement process converges in reasonable time. So yeah, so your question for the multi-unit, for the unit demand case, I think I have a satisfactory answer already. For the multi-unit, your question is important, and I don't have an answer right now. If you do have someone who, some other paper to suggest that they can mention regarding that, I would be very glad.
No, not from the top of my mind, but thank you very much.
All right.
So I have another question regarding the prices and this result with Balbusanov. Basically, what you do is you reduce the problem, or you transform the problem to one problem with positive coefficients. Okay.
Yeah.
What's the relation with the prices of each constraint with the Lagrangian?
The shadow prices.
The
idea of shadow prices, right? The Lagrange coefficients, right? You mean that? Yeah. They are in the slides. I didn't say it. Sorry for that. But yeah, they are related to the shadow prices of the constraints.
But the one that you reduce to this lower contour set. Okay.
Yes.
The one that
once you pre-process the constraints, then the shadow price associated with its constraint is what matters.
Okay, good. And I'm just curious. I think that you don't have the slides from the roommate problem, okay? But I was thinking about how could you get the positive coefficient.
This was rather complicated. There is an old paper by. So let me see. So going this in detail. But let me just tell you, Edmonds, 1965.
This
characterized the set of feasible allocations in the roommate problem.
Yeah. Okay. But this is the one, the paper with Edmonds. Okay, this is the maximum weight and all that stuff. No, because it's I think that I had some curiosity about the kind of stability that you can get in this in the roommate problem. It's similar to what Antonio was asking about the rural problem. Okay, the point is that in the roommate we know that the core is empty, there are no stable allocation, but you find a stable set in probabilistic.
But if in the roommate problem, you can get a stable allocation just by displacing the constraint. Because as long as you allow one individual to remain by itself, or more than one individual to remain by themselves, you can relax the problem. So you get a solution. But I wonder about the roommate problem, if I may. What about if we have a room for three? I mean, can you handle complementarity?
I don't really know.
My question is can you handle complementarities in any shape or form?
No, coalition. So there it's an extension. It's coalition formation. You are talking about the coalition formation.
It's an
we have some sort of very short discussion about that. But the honest answer is we don't have a proposition characterizing. Here is the lower contour set.
Okay.
Even in section number 5, you can find it. There is when you talk about the roommates, and then later on, it shows coalition formation, and but it's just a paragraph. We don't have a result. We just say that it is doable. I think it is doable, but someone else has to do it. We have already treated several problems already.
Not sure it's doable, and let me tell you why. I'm probably wrong, but that's required that your preference have complementarities, and you're gonna have problem with the whole smoothing thing if you allow for complementarities. Am I wrong?
I see that. The value of the.
I mean, if you get rid of complementarity, then fair enough. I mean, if one roommate is one roommate and people are alike and whatever, but if I need to have
the coalition,
you are in the account problem. I mean, you don't get stability among people.
Good point. So in the next revision, this paragraph has to be modified.
Well, I don't know. I mean, there is this paper by Alcan of stability in the three-side matching market. So if you have a three-side matching market, then you won't get stability for free. You need to make constraints. So you can get stability in the roommate problem because you relax conditions, you relax restrictions, but I'm not sure that the triple problem it's going to allow you to do that. So
I see.
I mean,
so so maybe it was very superficial our appreciation of this applies to making pairs as making, and maybe it was very superficial, no? Because in principle, why not, right?
Because the moment that you have one more additional agent, you have complementarities, and complementarities will give you a hard time. You need to find a way to get rid of it.
Yeah. I see that.
You have to develop preference over sets, and the moment that you have preference over sets, if you go you allow all possible profiles, then you allow complementarities. If you allow complementarities, you are not there.
Yeah.
That's
okay. So this point we have to take it more carefully. Okay. Yeah, as I told you, we just devoted a comment to this going beyond pairs.
Fair enough. This is like a double, triple thing and it's off the point of the paper. So it's not. Sorry for that.
No, but it's good to note the limits of this model. Okay, this model is not unlimited. It's not solving everything. So we are happy that it's providing solutions for things for which there were issues even in providing solutions. Problem with sorry, but or even the rural hospital. How to model rural pseudo-markets with under the rural hospital problem. So we were very proud of this, right? But of course, it is not unlimited. It's not by far. I'm pretty sure that we will find more cases in which the model does not apply. Okay, no model is general enough. You know that.
So we have more papers then. Okay.
More papers. Exactly.
So I think that it's time to close, and I thank again Antonio for his beautiful seminar.